complexity of somewhat approximation resistance predicates. Please.
So Madhur will talk next, and his result is slightly more complicated, so I thought that I would present this smaller, cuter result first. So the main statement of the result is on that board. It's just a dichotomy theorem for CSPs. In the morning, Suan presented his result on CSPs, and he talked about approximation resistance. So I will give some context to those results, and I will present my results along with that context. So this is how the talk should go. I will present the conditional version where we assume P not equal to NP, then the unconditional hardness, which is what these hierarchy results are, the Lasserre and these sorts of things, and then I will give an overview of the proof in the paper. This last section I will probably skip because it's just a proof in the paper which we probably won't have time. And the paper is on ECCC. Yeah, so as many of you are familiar with KCSPs, you know that they are quite popular in theory, and they are mentioned in several academic contexts, most prominent being Schaefer, who proved dichotomy theorems for KCSPs, and we want to emulate the result of Schaefer for the case when the CSP, we don't want to decide the satisfiability of the CSP, but we want to decide the optimum value of a max KCSP instance for a given predicate F. And the problem of finding max KCSP is of course NP complete, and the instance is, so this is essentially the problem. Fi are constants, constraints derived from the initial predicate F. Alpha is just an assignment on the n variables. There are m constraints, and you want to optimize this sum, which is the expected value of your CSP. Now it is so let us call rho f as the density of the predicate f, which is just the number of satisfying assignments of f divided by 2 to the k, and we restrict ourselves to the Boolean setting because in the higher alphabet setting things are going to be much more complicated. Now we choose a uniform random assignment, and it will satisfy rho f fraction of constraints. So this is a rho f approximation algorithm, and we want to see if we can do better than this trivial algorithm. And Hastad proved that it is hard for XOR. So his result is just stated here, that it is hard to distinguish between 1 minus epsilon versus rho f minus epsilon predicates. And such predicates are known as approximation resistant predicates. So you can't beat the random assignment. So what about, so this leads to a natural question, what about predicates other than XOR? And so F is said to be support a probability distribution mu if so and so condition is satisfied, and a linear predicate L corresponds to assignments L inverse 1 which form an affine subspace of F2. And K-XOR is a linear predicate, and so now we generalize linear predicates into what is known as well-distributed linear predicates, which are linear predicates which support pairwise independent distributions on the assignments mu. Now, as Suan said, KXOR is a linear predicate, and it's also well-distributed linear predicate. And this is his result stated in this notation, that for k greater than equals 3, epsilon positive, L a well-distributed linear predicate, then L is approximation resistant. This we saw today morning. And the general question is, which nonlinear predicates are hard to approximate, assuming P not equals NP? So let's define a weaker notion, which we call tau resistance instead of approximation resistance. And while approximation resistance asked for 1 versus rho gaps, we ask for tau versus rho gaps. And we will address this weak version of our original question. So essentially our question is to characterize tau f minus rho of f for a given predicate f. And so that's approximation resistance in the top, and this is tau resistance. And as Hastad already investigated tau resistance, he introduced somewhat approximation resistance where he studied predicates which are tau resistance for any tau greater than rho of f. And tau resistance is just a more precise terminology. And we are able to characterize tau f minus rho of f up to a factor of k to the 5. If you just go over the statement of the theorem, it will be clear that tau f minus rho of f is completely characterized, but we will come to this. So let Q be the set of quadratic predicates, that means predicates with no Fourier mass at level 3 or above. This is an example, and these two are the results of Hastad, that if f is not in Q, then f is resistant, somewhat approximation resistant, and if f is in Q, then it is not even somewhat approximation resistant. And the algorithm for this, we will actually, our algorithm for tau resistance will actually build on this algorithm. Yes, so this is the main theorem. So in the first case, we just say that if f is bounded, if f is far from Q, the class of quadratic predicates, if it is so far, then tau f we show to be, we lower bound tau f to be greater than equal to rho of f plus 1 over k to the 5. Otherwise, f is close to some quadratic, and let us call that quadratic g. So if g monotonically dominates f, then we actually give an algorithm, we upper bound tau f. But if the g does not monotonically dominate f, then we again give a lower bound for tau of f. So these are the three cases. So what is striking about this result? So to prove our three cases, the proofs are not very complicated. They are pretty simple, but this statement is very simple, and there are no such simple dichotomy statements. Very few. I mean, what we saw previously, Hastad's statement was one, but there are other dichotomy results, and for example, there is one with Ostrin and Court for partite CSPs, and they are very complicated statements. Madhur will present one which is also a very complicated statement, but this statement, it's very intuitive, and this is sort of the gold standard which one could hope for to prove for, for approximation resistance. So we would want such an intuitive classification of all approximation resistant predicates. So
can you say something about the K factor?
Okay, so this k greater than equal to k naught. So k naught is some constant. It's pretty large in our proof. It's like double exponential, but I think it's an artifact of the proof technique here, because we rely on this Freudgut-Junta theorem for some cases. That's why it grows double exponential, but it's just an artifact, and probably with a different proof technique, it will probably be just exponential. But yeah, so we are dealing with CSPs of large arity. We should always keep that in mind when we. Is that okay?
I mean, it just looks.
Oh, this k factor. Yeah. So in all of these cases, you should think of the statement as characterizing the gap tau f minus rho of f. Yeah, so and this tau f minus rho of f is within k to the 5. Now, why I get k cube and why I get k, that's because in each case the proof method is completely different. That's why all these k factors are different. You will see. Yeah, so essentially this is a summary of whatever I thought was relevant. This is the past, what was known as far as somewhat resistance is concerned, and this is what this paper shows. Okay, so let me just say something about unconditional hardness, because I think it is at least as important as conditional hardness. So here we don't assume P not equals NP, and we work with weak models of computation. And we use these STP and LP hierarchies as our model because these algorithms, so any model is interesting if you can get non-trivial algorithms from it. And both LP and SDP hierarchies give non-trivial algorithms for max k CSPs for some predicates. So there are results by Haast, Charikar, Makarichev, and so on, which and there is one by Trevisan, for example, which actually beats the random assignment for some predicates, for some sparse predicates, and that's why LP and SDP hierarchies are a good model to study, and lower bounds against rounding algorithms are important. In this setting also you can study the hierarchy of Lasserre, which is the strongest SDP hierarchy, and you can define approximation resistance as getting gaps of 1 versus rho. And if you fail for Lasserre, you could substitute weaker hierarchies like LS plus. So for example, in this setting, the counterpart to Hasta's result is this result by Schoenebeck, which shows that max k XOR is approximation resistance, where this now approximation resistance is defined in this sense. And then the counterpart to Chan's result is the result by Madhur, which shows well-distributed linear predicates are approximation resistant. And this result was already known in 2009, while Chan's result is much more recent. I don't know if this inspired that or what, but so, and now you can ask the same question, which nonlinear predicates are hard? And let me just say that not only can you substitute weak hierarchies like LS plus, in particular you could substitute any proof system you wanted, and you could study these dichotomy theorems, and people have done, they haven't studied dichotomy theorems, but they have studied hardness of predicates in proof complexity. Okay, so now just like tau resistance, we have tau star resistance, where you work with this Lasserre hierarchy, linear rounds, and one resistance is what and the main theorem here for tau star resistance is exactly similar to the theorem with assuming P not equals NP, which is nice because we had to do very little work to get the same result. And this is what is known as far as Lasserre hierarchy was concerned, and this is what we prove. Okay, so now I will concentrate on this P not equal, assuming P not equal to NP, the conditional hardness result, but the results generalize to Lasserre in the same manner. I mean, the techniques don't really change a lot. So roughly, as I mentioned, that Chan and Madhu's result is just that well-distributed linear predicates are hard, and And let us call good predicates as those well-distributed linear predicates which have very few accepting assignments. So the sparse, well-distributed linear predicates are good predicates for us. And so if the accepting assignments correspond to the Hadamard code, then L is a good predicate. And if it corresponds to the Hamming code, it's not good. And now we want to translate known results about good predicates to weak results about all predicates. So for this we introduce the notion of tau correlation, which just says whatever is given. This is the definition, which essentially means that the accepting assignments of F and L essentially coincide to a large degree. So let's start. So in the first step, what we show is if F is tau correlated to a good predicate, then F is also tau resistant. And the idea is simply a reduction from phi L. We construct an instance phi F such that if phi L was greater than 1 minus epsilon, then phi F is tau minus, at least. The val refers to the value of the max k CSP, of course, and no case also. And from phi L we obtain phi F, and some calculations, some very simple calculations show that tau correlation implies tau resistance. And this is the summary of the last slide. So our next goal would be to characterize what is the best possible correlation you can have for a given F with some good predicate. And yeah, so this is, it could even be k for the right values of k. You just take the Hadamard code and slide it, and you will get 1 over k correlation. But we need better values when rho f is a constant, say. When I say constant, please note k here is not held to be a constant. When I say constant, I mean absolute constants. So now we will go towards our goal, which is to characterize the best possible correlation of F with some good predicate. And let us define gamma r as the Fourier mass above level r. So step 2, we show that rho f is greater than gamma 3f over k square. And this proof is by probabilistic argument, which is the proof in the last section, which I will not present. But eventually we will find that working with gamma is a bit cumbersome. So we will prove. So we prove this as a lemma in the paper, and this is step 2. So tau f will be greater than rho of f plus omega of gamma 3f over k square, where gamma is the Fourier mass over level 3. But for cases 2 and 3 in the main theorem, we will need to work with delta, because working with gamma becomes cumbersome. So we need to relate gamma to delta, in particular gamma 3. And here is where we lose. We show this result that gamma 3f is related to delta within a constant factor. Recall that Q is the set of quadratics. And the claim is similar to the theorem of Friedgut, Kalai, and Naor, which deals with gamma 2f. And our proof of this fact used just the theorem of Friedgut, and we thought it was new, but apparently this result is also known from a paper of Kindler and Safra, an unpublished paper of Kindler and Safra. I mean, it's not stated in this way there, but a look at their proof essentially convinces us that it follows easily from that result. And so steps 1, 2, and 3 together prove tau f greater than equals rho of f plus 1 over k to the 5 essentially. And all that remains is case 2 and case 3. So case 2 is a lower bound, and case 3 is actually an algorithm. In the unconditional setting, we would get tau star greater than this from the same steps. So in step 4, which is case 2 of the theorem, we want to lower bound tau f as rho f plus 1 over k, and this proof is a bit technical. It's essentially a reduction using well distributed linear predicates, and it's just a bunch of calculations which are quite simple, but I will not give the calculations in this talk. I defer to the paper. But essentially this reduction directly from Chan's result is enough to prove tau f greater than equals rho of f. And one thing about this case is that even though gamma 3f is small, we are able to lower bound tau by rho f plus 1 over k, which means that gamma 3f is not enough to characterize tau of f completely. And finally the algorithm, which means the upper bound for tau of f. So we are given rho f plus epsilon satisfiable instance, and the SDP rounding algorithm, which is based on the algorithm of Charikar and Wirth, will output a rho f plus c epsilon over k square satisfiable assignment, and which means of course that tau f has to be less than or equal to this. So the result of Charikar and Wirth, it gives rho of f plus c epsilon essentially, when you know that your CSP is rho f plus epsilon satisfiable, and so that should be G, not F. And now we substitute, so now here is a simple algorithm. We substitute G for F in our max k CSP instance, use the algorithm of Charikar and Wirth. Then whatever assignment it outputs, you want to take that assignment and use it as your assignment for max k CSPF. The only problem is that remember that now G monotonically dominates F, so which is the last case, and so what may happen is the algorithm may output some assignment which does badly on every constraint in the CSP, and while max k CSP G may have a high value, max k CSP F has a much lower value. We can correct this. What we do is we introduce an extra step behind the Charikar-Wirth algorithm. So whatever assignment Charikar and Wirth output, what we do is we take it as an advice set, and with a small probability we take that advice, and with a large probability 1 minus 1 over 2k, we flip the assignment in a random fashion, 0 and 1 with equal probability, and this correction actually works. And the proof is not very difficult. It is again just an analysis of the expression of the expectation, and you will get this after a little bit of calculations, which again I defer to the paper. So this finishes the outline of the main theorem, and I will stop here. If there are the open question is obvious. Characterize tau as best as possible for constant values instead of values depending on the arity. Thank you.
Questions or comments? We'll have a break until 3:40, and then we'll have the talk that was scheduled to be now, but which will sort of be. Well, we thought this order was better. Okay, thanks again.